So today we will be learning about coordinate bashing, which is a technique which is applicable in geometry problems, usually in 2 dimensions. So for 2 dimensions, the Cartesian coordinate plane is formed by taking two axes that are perpendicular, which we can call the x-axis and the y-axis. And then each pair of real numbers, x and y, corresponds to the point that is formed by taking the origin, shifting it by x to the right, and by y upwards. And the reason this is applicable to contest geometry is that you can represent points given in the problem by coordinates, which you can translate as you want to make it convenient. And then you can directly compute points instead of looking for more abstract properties. So some standard facts about coordinates are going to be listed. One is the distance formula, which is basically just the Pythagorean theorem. The distance between x1 and y1 and x2, y2 is x2 squared minus x1 squared. Wait, no, I mean x2 minus x1 squared plus y2 minus y1 squared. And the equation of a line, there's many ways you can express it, but the one that's usually the most important is as y equals mx plus b, where m is the slope of the line and b is the point at which it intersects the y-axis. And a nice thing to know when you need to deal with angles in the problem is that if the line forms an angle theta with the x-axis, then m is equal to tangent of theta. There are also lines of the form x equals something. Here we can sort of think of it as m equals infinity, and indeed that it forms a right angle with the x-axis. There are other formulas as well, such as the shoelace formula, and it gives the way to find the area of a polygon. I'm going to just give it for 3 points and explain how you can generalize it. So if you have points x1, x2, sorry, x1, y1, x2, y2, and x3, y3, then the area formed by these 3 points is 1/2 of, you can think of this as the determinant, but I will explain what it concretely is later. So we can write x1, y1, x2, y2, x3, y3, and then x1, y1 again at the bottom. And how we compute this is by, we have pairs x1, y2, x2, y3, x3, y1, which go one right and one down, and those have positive terms. And then we also have things that go one right, one up, and these are counted as negatives. So the area is 1/2 of the absolute value of x1, y2 plus x2, y3 plus x3, y1 minus x2, y1 minus x3, y2 minus x1, y3. And here we use an absolute value signs by convention, although sometimes you might want to consider whether the area is positive or negative. But that is not something that is going to be needed for this lecture. And you can also generalize this to more points, but it very rarely comes up because, and even if it does come up, you can do it by just splitting into several triangles. But how you generalize it is, if you have more points, let's say x4, y4, x5, y5, now we have to ensure that these are in either clockwise or counterclockwise order. And then we can do the same thing we did before, where we list all of these points and then we add x1, y1 at the bottom. Then there are some other formulas that show up every now and then. One such formula is the distance from a point to a line. And if the line has equation ax plus by plus c equals 0, which is a rearrangement of the form given previously that can be more convenient to work with when there's more symmetry between x and y. And if you have a point, let's say x0, y0, then the distance from x0, y0 to the line, which we can think of as the length of the perpendicular segments to it, is the absolute value of ax0 plus by0 plus c over root a squared plus b squared. And this is tricky to remember. When I first learned this, I kept confusing myself about whether the denominator was square root of a squared plus b squared or square root of x0 squared plus y0 squared. So I don't think this formula is too useful, although it may have some applications. So it's not important to memorize the formula itself, but it can be helpful to know that if you ever do need to find the distance and you don't remember the formula, you can do it by considering the triangle formed by the 3 points, finding its area by shoelace, and then we already know this length, which is from the distance formula. And then the area of a triangle is 1/2 times the base times the height. So that would give that the distance is this determinant divided by this point and this point's distance. And now we can spend some time thinking about how this applies when we're not in 2 dimensions, because often in higher dimension geometry that appears in contests, being able to chord bash is very helpful if you cannot visualize it. So here, the distance formula remains the same. We would have, for example, in 3 dimensions, x2 squared minus x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And this is basically just Pythagorean theorem in many dimensions. The equation of the line is complicated, and in general, something of the form ax plus by plus cz plus d equals 0 is a plane. I'm going to move this. So usually the equations of lines in higher dimensions are not very nice to work with. For shoelace formula, you can derive a similar result for 3 dimensions, but it doesn't show up very often, so I'm not going to go into it. And the distance from the point to a line, you can replace the distance from a point to a plane and do something similar. And now we can think about when chord bashing is a useful technique, because sometimes geometry problems have simple solutions without bashing, and if you do try to bash, you can sink a lot of time into something that's too complicated to do in contest. So sometimes when you don't want to, some things you want to avoid are that you don't like square roots. So if you have something like square root of 3, which comes up by itself, that can be fine. But in general, the distance formula, for example, has a square root. And if this doesn't turn out to be an integer, it can be too ugly to work with, and the batch would likely not be feasible. And so this is something you want to avoid. Lines are good. And this is because they're just linear equations, and you can get messy rational expressions if you have to keep intersecting them, but these usually don't become too ugly. And I should also mention the equation of a circle can be found basically by distance formula. You have a center HK, and you have that this distance is equal to some r, and then you square both sides to get the equation of the circle. Circles are usually not good unless you are intersecting either a circle with a line and you know one of the intersection points. Because then, if you think about how you would intersect a circle in a line, you have a quadratic expression in x and y, and you're plugging in something linear. So you would end up with a quadratic with potentially annoying coefficients. And if this is a general quadratic, you would end up getting back into square roots because of the quadratic formula. Unless you already know what one of the intersection points is, because then you can find the other intersection points in a variety of ways, one of which would be applying Vieta's formulas on the quadratic. And another scenario in which circles can be fine is if you are intersecting two circles and you only want to think about what the equation of the line through these two circles is. And the reason this is something that can be important to consider is that if you define the power of a point P as taking any line through it, considering the intersections A and B with a circle, and defining the power to be PA times PB, not only is this the same no matter which line you choose, but also this line is the set of points which have equal power with respect to the two circles. Another time in which circles can be nice is when you only need to care about the circumcenters. Because if you are taking the circumcenter of 3 points, you are essentially just taking the intersection of their perpendicular bisectors. And this is the intersection of some lines, which, as we saw before, is not too complicated to deal with usually. And this is a good time, I think, to recall two things that follow from what we have seen, follow from the properties we have seen before, which are that the midpoint of x0, y0, and actually x1, y1, and x2, y2 is x1 plus x2 over 2, y1 plus y2 over 2. And if two lines are perpendicular, their slopes multiply to -1. And this can sometimes be a problem because here you have a perpendicular line, which means that if the slope of the side is large or has annoying factors, then you could get an ugly rational slope that makes the expressions too nasty to work with. But even then, it's significantly better than the square roots because at least everything you're working with is rational. Coordinates are also good for area because of the shoelaces theorem and shoelaces formula, and that maintains the rationality of whatever you are finding. In general, a rule of thumb is that you want to work with rational things because otherwise it's just too hard to compute. And some general tips about bashing are that aside from what to think about and what to avoid are that first of all, some geometry problems are inherently better to bash than others. And this can even go to whichever shape you're working with. So most geometry problems that you would chord bash have some sort of triangle in them. And a right triangle is definitely good because then you can set the two legs to be the x and y axes. And an isosceles triangle is good because then you can set the base and I forget the term, but the median of the opposite sides. So like this line, I'm just gonna write it as median. So for the right triangle, you set the legs as the axes. And then an equilateral triangle is a special case of an isosceles triangle, so it's also usually good to work with. But some scalene triangles are also nice to work with. The most common one is the 13, 14, 15 triangle. And the reason is that this has a very nice property, which is that if you draw it like this, and you take the height, and sorry, you take the altitude, you can find that the height is 12, and the base splits into 9, 5 and 9. So if you define this point as the origin usually, then this becomes 9, 0, which is a nice coordinate. This becomes 0, 12, which is also nice. And this becomes -5, 0, which is also nice. Because these are all relatively small integers. Several other triangles also work well, but not as much as the 13, 14, 15 triangle. In general, you want, whenever possible, you want this height to be an integer. And you also especially want these numbers to be integers. It can sometimes be feasible if one of them isn't, but it's much less likely to work out if you have to deal with the square roots. And if you are just choosing axes, you want, like, if it's not a right triangle or an isosceles triangle or a 13, 14, 15 triangle, and you're just trying to decide how you configure your bash, you want as many points to be on either axis as possible. And this is not a concrete rule or anything, but it's just helpful because if a point is on an axis, one of its coordinates is 0, which greatly simplifies calculations. But also, on this note, two bad points are better than one very bad point. Bad meaning that the coordinates are messy. So for example, if you have a way to set it up where you'll get 2 points which each have some square roots in them, but if you set it up in a different way, you'll only have 1 point, which has a sum of square roots in it, you would usually want to go with the first option. In fact, I would say that if you can replace this 2 with, I haven't thought of this as a specific number, but any number within how many would usually show up on a competition problem, I would say that any number of bad points is better than one exceptionally bad point. And the last tip is something that you hear a lot when you're introduced to bashing, but it's hard to follow, which is that you should never turn your brain off. And this is in response to something many people usually say about bashing, which is that you write some coordinates and then you just stop thinking about the problem. You're just working through some computations. So you never want to fully focus on the computations. Um, and the reason for this is because although maybe this would save you some time if you need to work through a bash quickly, the downside is much higher than the upside. And this is for several reasons. First of all, many problems that show up on contests are chord bashable, regardless of how messy they are, if you have sufficient effort and time to put into them. But usually this amount of effort and time is not something you would have in contest, and it's better to not attempt these bashes that could take around an hour, for instance. So if you're just seeing that a bash is not working out quickly enough, you want to think about whether it can be feasible in the time, or if you should just give up on it. So know when to move on. And you should also start by thinking about the problem in a synthetic way. So you don't want to start thinking how can you coordinate bash your problem, because that can often prevent you from seeing some very helpful simplifications. And um, when another thing that I forgot to mention that relates to this any number of bad points is better than one very bad point is also that you never want to have to introduce variables if you can avoid it. And I say this if there's something like you can't explicitly compute a point, but you know it has to satisfy certain properties. So you let the point be A, B, and you write out a system of equations for the properties it satisfies, and you try to work with that. This is almost always too messy to work with. And sometimes this is not something you can execute even if you had the full contest duration to work with. So unless it cancels almost immediately, you should not try to use a sort of system of equations in some unknowns that you're introducing. And the last thing on this note of thinking synthetically is that I think the primary and best use of something like coordinate bashing is to try the problem synthetically. but you watch for when it seems chord bashable. And when it seems chord bashable is a very vague notion that you can sort of develop through a lot of practice, but also no one really wants to practice chorded and bashing that much. So in general, when you're thinking, does this seem chord bashable, you should usually focus on things like, will there be a very bad point? Will there be too many bad points? Will I need to introduce a variable? And oh yeah, will I need to have square roots in it? Are there too many circles? And if you see that too many of these are the case, then it usually isn't chord bashable. So what this means essentially is that you're working on the problem without trying to bash it. But if you ever see something that can reduce it to a bash that is feasible, then you would go for that. And I believe the first problem I'm going to demonstrate is a good example of this, but it's also a good example of the advice to never turn your brain off. So this is from last year's AIME in number 12. And you can note that there's an equilateral triangle. Oh, I also forgot to mention that usually angles are not good to work with in coordinate bashing because other than this one, where is it? Okay, other than this one relation with angles, basically everything is in terms of lengths and perpendiculars. So angles are usually not helpful. But one thing to remember is if you have an angle bisector, it can be feasible, but you will need to use the double angle tangent identity because then you can think of the tangent as a slope and you can find the slope of the angle bisector. Anyway, back to the problem. So we have an angle condition, but we do have an equilateral triangle. One thing to mention about the equilateral triangle is that we will have a square roots in it because if we think about it as this is the x-axis, then this height is 55 over 2 times the square root of 3, and this is an ugly number. But also, the square root of 3 is the only square root that shows up in the equilateral triangle. So as long as nothing else is too messy, it should be feasible. The problem is that there are messy things. There's this angle condition that does not make too much sense to interpret in coordinates. And I'm going to draw a diagram first. So you have a point A, C, and B. E is on AC with CE equals 30. F is on AB with AF equals 40. And D is on BC with BD equals 7. And then we have a point P such that we have a bunch of equal angles. And you can see that this condition is clearly not true for my diagram, but I guess that's not too much of a problem because we don't need to notice anything about the diagram as we don't need to think that 4 points look cyclic or anything. So the key point of this problem is to start by thinking about it synthetically. And during the AIME last year, I made the huge mistake of trying to incorporate this angle condition into a complex bash, which is basically coordinate bashing, but you replace x, y with x plus yi. And I sort of knew that this wasn't really going to work out, but I was quite inexperienced at the time, so I thought that if I spend enough time on it, it can work. And I think I spent around an hour on this before I decided that I was not going to finish the complex bash in time. And then only then did I try to think about this problem synthetically. And because of this angle condition, right now it is hopeless to coordinate bash. So let's just try to solve this problem synthetically. We have these equal angles, and let's say they're all theta. Since the sum of the angles on a line is 180, angle AFP is 180 minus theta. But the condition for a quadrilateral to be cyclic is that the sum of opposite angles is 180 degrees, which means that AFPE is cyclic, and you're going to have to pretend that's a circle because my diagram is a bit inaccurate. Similarly, BFPD is cyclic, and CDPE is cyclic. I'm going to erase these because these are neither good circles, and they also obstruct the diagram. And we want to find the tangent squared of this angle. And that's also the same as finding the tangent squared of 180 minus the angle. It doesn't really matter too much which we do. But the main point is that if we think about what the tangent means in coordinates, that is the square of the slope PE, if we set this to be the x-axis. So what have we seen? We have seen that this quadrilateral is AFPE, BDPF, and CEPD are cyclic, and we want slope of PE squared. And now it is a reasonable time to start thinking about how we can coordinate bash this problem, because now that we've found these cyclic quadrilaterals, we have entirely removed the angle condition. The problem is that circles themselves aren't too nice to work with. But these are circles that each intersect at 2 points. For example, these two circles intersect at P and F. These two intersect at P and D, and these two intersect at P and E. And as I mentioned before, intersections of circles are nice because they are what's called the radical axis, which is the locus of points where the powers with respect to each circle is the same. And what that means is that if we say O1 is the center of AFPE and O2 is the center of CEPD, then PE is perpendicular to O1, O2. So what we really want is 1 over slope of O1, O2 squared, and it suffices to find the slope of O1, O2 to do that. And now we have two quadrilaterals, both of which involve P, but also three other points. And another thing that was fatal about the complex bash I wasted way too much time on during contest was that the way I tried to go about it was to introduce a variable P, write out these conditions in terms of P, and try to solve the system of equations to determine what this point P actually is. So we do not want to do that because, as I mentioned before, adding new variables increases the complexity of the values by too much. But these circles also have three other points on them, and we know what these points are. So we can say that the midpoint is 0, 0, A is negative 55 over 2, 0, C is 55 over 2, 0, and B is 0, 55 over 2 root 3, because those are the distances from each point to the midpoints in an equilateral triangle. And we can also write out F, which is 8 over 11ths of the way from A to B, which means we can write it as 40 over 2 root 3 and negative 15 over 2. I actually, I'm not sure about this because I haven't done this in a while, but basically you're taking the weighted average of these 2 points, so it should be 3 times A plus 8 times B over 11. So yeah, this should be right. And then D is, okay, it's going to be hard to draw all of these on the diagram, but D is 7 over 55 of the way. So it's 48 over 2 root 3 and 7 over 2. And now we want to find the circumcenter of first, what's it called? AEF. And the circumcenter is the intersection of perpendicular bisectors, and the perpendicular bisector of AE is the line x equals negative 55 over 4. Now we just need to take one of the other lines. Actually, I am not being very careful with this. I forgot that this is not E, this is the midpoint. E is actually the point which is 25 from A and 30 from C. So it is negative 5 over 2, 0. And the perpendicular bisector is the line x equals negative 30. We can now just pick one of the lines AF and EF and find its perpendicular bisector. So let's go with AF. The slope is root 3. And you can find this by doing this minus this over this minus this. And the midpoint is negative 15 minus 55 over 2, which should be negative 35 over 2, and then 40 over 2 plus 0 over 2 times root 3, which is 10 root 3. So if you take the line perpendicular to AF through the midpoint, you get y equals negative 1 over root 3 times x plus something. And if you substitute the midpoint in, you got 10 root 3 equals 35 root 3 over 6 plus, let's say c, and then c equals 25 root 3 over 6. Now, intersecting this with line AE, and this is one of the benefits of A and E being both on the x-axis, we have that x equals negative 30, so y equals 30 over root 3 plus 25 root 3 over 6. And since this only has one Taylor square root in it, we can calculate it as 10 root 3 plus 25 root 3 over 6 equals 85 root 3 over 6. And we don't have too much time, and the other calculation for CED is essentially the same thing, so I'm not going to do it now. But basically, you find the midpoint of line CD, find the slope of it, take its perpendicular bisector, and intersect it with the line x equals 25. Then you have then we would know x01 equals x and y, which x1 and y1, which are negative 30 and 85 root 3 over 6, and O2 equals x2, y2, which are I did not calculate them here, but you can find them in the same way. And then the slope is y2 minus y1 over x2 minus x1. And if you calculate this, you should get 1 over 5 root 3, which means the answer is 5 root 3 squared equals 75. And the main takeaways about this problem are that you don't want to immediately jump into an attempt to bash a problem. Instead, you want to try seeing how you can work with the condition and only switch over when you know the problem is feasible with bash. You don't want to deal with angle conditions in a bash, and you want to make simplifications from angles from circles into just lines and perpendiculars, because that is fundamentally what the Cartesian coordinate system is. And also there's the idea about you do not want to introduce a variable for p, because then it becomes too complicated. And another thing we notice from this problem is that the computation of a circumcenter of these um, not very nice but also manageable points is not too messy, and it's something we can do within the contest time. And this bash does take quite a while, but nowhere near how much time you could spend if you tried the same thing without working with the angle conditions from the start. And now I'm going to show another problem that furthers this point. So here we have a right triangle AB. I did not mean to increase the thickness. A right triangle ABC, and the foot of the altitude from C to AB is D. And then we have the midpoints L of AD, M of DC, and N of CA. We know that CL equals 7 and BN equals 12. I'm going to not draw this in the diagram because it makes it too cluttered. We want to find BN. And here we can't chord bash it as is too nicely, because we have this point, we have this point, and then L and D are some combinations of them. And taking something like the distance of CL is too hard, as well as the distance of BN. However, we can think back to when we decide how to set up a problem. Even though a right triangle is good because we can set its legs as axes, the most important thing about this is that you want as many points to be on either axis as possible. Here, the points we are working with are A, L, D, B, M, C, and N. Of these, everything but N is on either AB or CD, and these are perpendicular. So then we set D as the origin. Let's say B is negative B0, A is A0, and then it's possible to compute basically by computing the slope of BC and the slope of AC, that C is the point 0 times the square root of AB. And I mentioned several times that you usually do not want to see the square root here. And that's why when I originally was coordinate batching this problem, I instead put a squared here, b squared here, and did not have the square root in it. But this is a retroactive decision I made after realizing that the only actual involvement of C is that the length CL is given, and also that this midpoint n is dependent on it. Its coordinates are a over 2 root ab over 2. But if we think about what we're doing with these points, in both of them, we're finding the distance from it to something on the x-axis. So whenever we see these points, the square roots are going to be squared and they're not going to be too problematic. So let's write out the conditions on the lengths. And I say that usually you don't want to introduce variables like a and b, but here no information about any of the side lengths is given, and you're only introducing variables for the fundamental points of the problem, so it's not as bad as usual, although it is still annoying, as we will see. So CL is 7. That means CL squared is 49, and then we multiply that by 4 for convenience, because this is a over 2, 0. And that gives that a squared plus 4ab equals 196. For bm, which is 0 root ab over 2, this also depends on c, I forgot to mention, but again, it's going to disappear immediately. This time we get that ab plus 4b squared equals 576. So yeah, not particularly nice. And this is one of the reasons why, in general, you don't want to deal with adding these variables. And this also serves to indicate that sometimes, even if something seems conceptually wrong, you should write it out and spend a minute or less thinking about it to see if anything nice happens. Indeed, here, if we multiply the second equation by 4 and add these, it just becomes that a plus 4b squared equals I forget the calculations, but it should be 4 times 49 plus 576. And 49 plus 576 is 625, which is 25 squared. So a plus 4b equals 50. In fact, the first equation is just that a times a plus 4b equals 196. And the second is that, wait, this seems slightly off, but I guess there's, actually no, this is right, yeah. And then the second is that b times a plus 4b is 576. So then we know that a is 98 over 25 and b is 288 over 25. And here you might, if you're quite watching this, you might stop and say this is way too ugly and it's going to be better to try this synthetically and restart. But for demonstration's sake, I'm going to finish this. The length bn squared times 4 is 2b plus a squared plus ab, which is, we can write this as, so if we divide it by both sides by 4 at the start to avoid having to deal with that later, this becomes 49 plus, wait, it should be 49 plus 288, but I think it's supposed to be 49 plus 144. Um, okay, I'm just going to write it as 193 over 25 squared. I don't remember exactly what went wrong here, but that's what I remember getting when I did the bash. And then AB becomes 49 times 144 over 25. And if you calculate this, this is like some 3-digit number. You can actually, it's not too annoying to calculate if you do it as 200 minus 7 squared. Then you get 40049 minus 2800, which is 371 um 37249. I'm gonna quickly check that with my calculator. Yeah, 37249. And then 49 times 144 is 7200 minus 144, which is 7056 or something like that. I believe this term also might have an error, but yeah, it is 7056. And the point is that when you add these numbers, you should get 193 times 625 in expanded form over 625. And that gives the answer of 193. And part of the reason I chose this problem was because it shows that you should set up the problem to include as many points on the axis as possible. But another reason was that because of what happened here. When you have a bash that has too many complicated terms, it's very easy to cause some mess up here, like in 49 plus 288 and whatever went wrong with this term. And it's just way too hard to go back into your work and figure out which step you went wrong at. And this did work out at the end after I managed to do this batch after catching errors at least 3 times and computing a bunch of 5-digit numbers. But then I tried this problem synthetically later, and this was one of the things that made me stop chord bashing as my first instinct. Because the solution is you have, I'm going to draw it like this again. You have CBA, D, N, L, N. And because these are right triangles, the triangle BCD is similar to the triangle BAC, which is similar to the triangle CAD. And the lengths from the first point to the midpoint of the opposite side are BM, BN, and AM. So the ratio of these lengths is equal to the ratio of any of the corresponding sides of these similar triangles. And from that, you can solve the problem. This is much, much faster, much neater, and is one of the reasons why you should never default to trying to chord bash a problem, no matter how much experience you have with it. And this also shows that maybe if you miss this idea and you try to go for this coordinate bash instead, at any point, if you find a calculation error, it might just be better to abandon that attempt and continue working on this synthetic approach. Because even if this synthetic solution takes you 15 minutes to find, that still might be faster than bashing this problem. So the main takeaways are that you should be judicious about how you set up a problem. So how you choose axes. You should start synthetically and just work through the problem synthetically until you can't see anything else, while also keeping in mind, is this chord bashable quickly, and know what to avoid. Because if you struggle with synthetic geometry, which is a problem I usually have, sometimes looking directly for what synthetic simplifications can I make is too hard. But sometimes if you know that there is a circle and I want to get rid of it somehow, it's easier to think about what simplifications you can make. So if you know what you want to avoid, it's easier to go through the synthetic steps. But above all, the main takeaway is that when you are bashing, keep thinking about the problem rather than just your calculations, because there's just too many things that can go wrong with your calculations, and it's better to keep thinking about how you can find a better approach. So that is all for the lecture. Are there any questions? Okay, so I see a question that asks, how can you, what should you do if you're sure you can bash a problem, but you think you might be able to do other problems in the same time? If there is, so usually this sort of geometry bashing is by far the longest problem you would have to go through. So if you have ideas for other problems, that would usually be better than trying to start with a geometry bash. But if you don't see anything else you can do, and even even if you don't see anything else you can do, if you don't have a good idea for how you should bash, it's probably better to just try to check your work instead of spending way too much time in a futile bash attempt. Are there any other questions?
There is a question in Q&A. How long should you try to bash for?
Usually, I think the longest I have spent on a bash attempt without making progress is 5 minutes, which is a number that's dependent on your experiences. But I think that if you spend more than 5 minutes and you're at least not making progress, as in finding important steps or evaluate or calculating several points, then it might not be fast enough. For the AIME, there's an average of 15 minutes per question, so I think if you have enough time, you can probably increase that to 10 or 15 minutes, but if you are low on time, you might even want to see if you can do the entire batch in 5 minutes. So yeah, the main point is you should only try to bash as long as you are making concrete progress, because that shows that it's feasible. If you don't make concrete progress for something like 5 minutes, but this number is dependent on you, then it probably won't work. Are there any other questions?